This is a specification for one of nature's machines. Its design has taken 200 million years to perfect. Now the effectiveness of that design is about to be tested. Living creatures evolved in a world which is full of variety, extremes of temperature and terrain, land and water, marshes and deserts. To survive in this changing world, life has had to be inventive. To move around from place to place, animals have devised natural engineering solutions to their problems. As a recent arrival, man doesn't have some of the agility and speed of the animals, but he makes up for this lack of skill by the ingenuity of his technology. Surrounded by a protective shell, we can travel wherever we like, however hostile. Now our machines have taken us into space. We have built ourselves sophisticated manipulators, and the computer revolution allows us to sit back while robots do our work for us.
We're bringing it back to show. We're on page 186.
We use our robot devices to protect ourselves from hazards such as radiation, or to carry out the more boring and repetitive tasks in industry. But not all engineers are preoccupied with such mechanical tasks. There's a new breed of designers who see that biology has solved some of the problems we haven't.
Most people have in their understanding, I guess, the idea that machines can someday produce devices, carry people around, go into dangerous environments, do a number of things of value. In the shorter term, the reason we build these devices is to understand more about them. For example, how can you make a machine manipulate an object or assemble a pump? How can you make legs carry a vehicle around? There are a number of basic questions there which are of interest and which are studied either by building machines and observing their behavior, or taking biological machines apart and try to understand what principles underlie their operation and how they in fact do so well.
Wherever animals go and whatever they do, their movements are subject to the same laws of physics as any man-made device. We can often solve our own engineering problems by analyzing the successes of the other animals. Even the most advanced concepts, such as the variable geometry wing or swing wing, have been used by birds before man even existed. Certainly, it's in the air rather than on land that man competes best with nature's technology. Try designing a plane with legs, and you'll see why our flying machines have to have wheels and a smooth runway. Of course, biological engineering doesn't solve these problems overnight. It takes a year for this baby to learn to control its legs so as to carry an irregularly shaped body while keeping upright at the same time. everyday actions are far more complex than they seem. The two main skills of moving and manipulating require the collaboration of muscles and bones and, above all, a complex nervous system capable of learning from its mistakes. Like the hesitant stumbles of an infant, machines are just beginning to stand up on their own. But it will be several years before they develop the skills to cope with rough country like a man at the peak of his performance. When legs have carried the body to the site of action, arms and hands come into play. They have evolved to perform the most complex engineering operations, although again, the skills take years to acquire. The human hand is a hard act to follow. It is capable of exerting great force or delicately examining objects for their shape and texture. Faced with achievements like these, how close are engineers to building a robotic version of this extraordinary device?
Well, I don't think we can build a human hand for a long time to come. Even if you try to build a hand as simple as this or as complicated as this, whichever way you'd like to look at it, you find that it's a formidable undertaking. What we're really interested in copying are principles, not specific devices. We don't make things like biology makes things. We make things another way. What we elected to do was build a hand that had not as many fingers as a natural hand and not as many sensors as a natural hand, but something with enough complexity to provoke the working of people in the area of understanding grasp.
The Utah hand can be forceful or gentle. It can act slowly or very, very fast. The hand would be uncomfortably large if it had to contain all the muscular power it needed within itself. Like the human hand, tendons are necessary because the power source is some distance away. In this case, the job of the muscles is done by pistons powered by compressed air. The sequence in which the pistons operate is under the control of a computer. For sheer reliability, human tendons still have the edge. Self-lubricated and self-renewing, they are extremely difficult to imitate. Weight for weight, their elastic strength is greater than mild steel. Tendon technology is the key to the design of lightweight manipulators. Human tendons never wear out under normal use, but the synthetic tendons can stretch or break and have to be replaced from time to time. This arm uses wires that combine the roles of both tendon and muscle. The wires that run along the arm to the hand are made of a nickel and titanium alloy that contracts when it's heated. It gets hot when a current is sent along the wire, and this generates a force to move the hand. It's been built at Waseda University in Japan. Because the wires are so thin, the arm can be very light, and they are the nearest engineers have come to imitating the action of muscle fibers. The hand is a superb general-purpose tool, but in nature we can find manipulators that are sometimes adapted to very specific functions. Take the elephant's trunk, for instance. It is peculiar because it has no bones to give it rigidity. Yet if we look below the surface, we see a very ordered structure. First, there is a thick layer of muscles running along the trunk which can bend it in any direction. Underneath are spirally wound fibres to make the trunk twist. In the centre is a core of springy connective tissue around the nostrils. Radial muscles attach this to the surface. When these contract, the trunk gets longer. All these muscles are anchored in sheets of tendon. The result is a very flexible manipulator, precise and delicate when it needs to be, but capable of a wide variety of activities involving different amounts of force. The elephant's trunk is called into service for eating and drinking, grooming and mating, and it has a very sophisticated control system, which means it can be accurate even when moving heavy loads. For engineers, obtaining this degree of control over flexibility creates problems.
If you consider your hand, if you hold it out in front of you and then suddenly apply a load, your hand gives. For instance, if I want to take this book and suddenly drop it on this hand, then the hand gives. And the amount that the hand gives to the load is termed the compliance of this structure. And the sort of problems it causes, well, it can be both a problem and a feature. And the sort of problems that you might encounter is if you want to control this structure accurately at a large radius while carrying a heavy load. It's very difficult to make a very large manipulator which can carry a heavy load with slender proportions without it giving in some way. Similarly, you may want to actually build a manipulator with exaggerated degrees of compliance, and it then becomes very difficult to control that manipulator accurately.
The elephant's trunk was the inspiration for this compliant manipulator under development at Duke University. Imitating the muscle structure of the real thing needs some ingenuity.
This is a bellows, and bellows operate in such a way that when they're pressurized, they simply extend. And the amount of extension depends on the amount of internal pressure. So this behaves unlike a muscle that contracts. This expands, but this has a similar action if one considers reinforcing such a bellows along the side. If you reinforce it along the side, you can get bending out of this by when it's pressurized, the element goes around in this fashion, because one side cannot expand and the other side does. Now, in the animal elements, one side contracts and the other side remains the same, but it gives the same effect. So that's the analogy. A third element is a twisting element, and this gives wrist action. These have helical windings, and when this element is pressurized, it simply twists.
Air pressure in the segments is coordinated by computer to produce the movement. The compliance, or flexibility, means that an operator is still needed to give the robot information about size, shape, weight, and where to find the object. If it is put in the wrong place, the machine will miss. Nevertheless, there are real advantages to this inelegant-looking device.
I think there are three advantages to these robotic limbs. The first one is that they're fast-acting. The lighter weight something is, the faster it will move under a given set of forces. The second advantage is that they're relatively light in weight. They can carry much more than self-weight and payload. The third advantage is that these limbs are robust. They're similar to, when properly reinforced, automobile tires, which can withstand impact loads in the field.
Present industrial robots achieve precision by being very rigid, but this also means being very heavy. With a robot arm weighing 200 kilos, a load of only a few kilos can bend the arm too far. Compliant arms, like our own, can move accurately many times their own weight. This is just one reason for developing compliant arms for industry.
If you want to assemble something, then you have the problem of impacts with your environment. And when you have this sort of problem, when you want to impact one object on another object, for instance, if you are assembling, say, a watch, then you have to be able to control the sort of forces exerted, and the best way of controlling the forces exerted is to incorporate compliance.
This gripping device has got wire tendons running along inside the links of a flexible metal chain. The tendons pull the chain to conform with any shape. It is compliance that allows it to apply its grip with even pressure to any shape, even though it has no concept of the outline of the shape. It's one of the latest products of Japanese robot technology, and it can apply its grip with even pressure to any shape, compliant or not. This product gets its design from the pliable form of the snake. Snakes have bodies that allow them both to move and to manipulate with the same simple engineering design. An intricate and flexible skeleton is moved by hundreds of muscles to make a tube that can be rigid in some sections and bendy in others. Each segment of the snake is controlled by a separate section of the spinal cord so that it can carry out feats like this, clinging tightly to a tree with its back end while using its front like a flexible manipulating arm. For engineers who want to gain access to tight corners, snake technology has been a fruitful source of ideas. The Central Electricity Generating Board has been working on this robot arm to help repair nuclear reactors. Each segment follows the movement of the one in front, and so the operator only has to point the head, and the robot ensures that the rest of the body follows the same path. With closed-circuit television for eyes and a toolkit as fangs, the snake robot can be inserted through a convenient hole to reach the tight confines of the reactor. The serpentine movement of a snake converts sideways motion of the segments of its body into a fast slither forwards by pushing against the ground. The regular bends are produced by sequences of nervous impulses passing down the spinal cord. The principle is easier to see in this Japanese machine. Although it's got wheels, they are not powered. All the forward movement comes from the bending of one segment in relation to the next one. Small electric motors are controlled to move slightly out of synchronization with each other. This generates a series of bends that travel backwards along the snake's body. As the bends move backwards, the snake moves forwards. By changing the order in which it moves its sections, the snake can generate bends to cope with any type of narrow, irregular path, such as pipes.
Could I get your attention, please? There has been a state of emergency declared on 3 mile hour.
When safety systems failed here, it hit the headlines. Not so obvious was that a mobile inspection robot was used to reduce hazards to personnel trying to contain the emergency. Bomb disposal teams use robots with wheels, but there are plenty of situations where only a human with legs can go. This fact is not lost on the military, and that's the clue to the next key development in robot locomotion: machines with legs.
The military has been interested in legged locomotion for quite some time, at least 20 years actively that I know of. The reason is that 50% of the dry land mass of the world is impassable to wheeled or tracked vehicles of any military design.
Enter the Adaptive Suspension Vehicle, a six-legged juggernaut developed at Ohio State University for the United States Department of Defense. Ultimately, production versions of this prototype will carry men and equipment through dense forest, marshes, and boulder-strewn hillsides where even tanks cannot go. As we'll see, the work going on around the world is producing a new generation of walking robots that embody many principles of biology-based engineering. The propeller, rotating on an axle at the top of this tiny creature's body, is nature's only known attempt to invent the wheel. And yet, our man-made world is full of wheels. Has man improved on nature's technology? Not really, since we've had to invent roads for them to run on. Nature's solution, legs, is still the most versatile way of getting about on almost any surface, however rough. One problem with wheels is that they have to be large enough to straddle the dips and holes in any rough surface. Another is that they are not much use for the soft surfaces that cover much of the world.
In soft soils, legs are much more efficient than wheels. They can transfer more power into the soil per onboard horsepower than a wheeled vehicle can. We've designed this machine so that the relationship between the operator and the machine is very analogous to that between a horse and a rider. The operator tells the machine through the hand controller which way he wants to go and how fast he wants to get there. And the machine does almost everything else, especially as far as where to place its feet and which ones to cycle, so that the machine can crab walk as it's moving forward. But equestrians can teach horses to do that on command too. Can teach a horse to walk sideways and even backwards. Our machine walks backwards much more readily than a horse will walk backwards. But that's because our machine isn't as smart as a horse and doesn't understand that it could trip and fall. The ride quality is somewhat similar to a horse. It tends to be a little bit bumpy, but we could smooth that out if we just had faster computers.
Like a monstrous insect, this machine makes stately progress at 8 miles an hour on hydraulically powered legs, and it's all run from one motorcycle engine. Nature has been perfecting the design of legs since the first creatures crawled out of the sea 400 million years ago. There are many different designs of legs depending on the size and weight of the creature. Some animals have a lot, synchronized so they don't interfere with each other. Some smaller and lighter animals have widely spread legs to prevent them from toppling or even being blown over. Larger animals have their legs placed under the body like pillars to support their weight. For fast-moving animals with fewer legs, balance is more of a problem. Having lots of legs gives you greater stability and more traction. Choosing the most appropriate number of legs and the best way to balance on them is the first problem facing designers of walking machines.
There are two kinds of balance, active balance and static balance. In static balance, also called passive balance, all that matters is the positions of the legs and the feet with respect to the body. If you took a walking machine that was walking with passive balance and froze all the joints, the machine would just stay in the position you left it, and it would be passively stabilized. It would balance itself pretty much the way a chair or a table balances. In active balance, this is not the case. And an actively balanced system would tip over if you just maintain the configuration. For instance, I'm going to balance this ruler on my finger, and if I were just not to move my finger, it would tip. And in order to balance it actively or dynamically, I have to move the point of support back and forth in response to the tipping motions and the travel of the body. So in a dynamically stabilized system, there is sensing of the motion of the body. That's the key thing, the motion. And in a passive system, the motion of the body is so slow typically that it's not important.
Take the humble tortoise. It tries to maintain a static balance. If it becomes unstable while it's walking, it will scrape the ground before it can correct itself. Because it's moving so slowly, this will bring it to a grinding halt. So what it does is to move only one leg at a time, leaving itself reasonably stably balanced on the remaining three. Its walking pattern is a moving tripod, a sort of peripatetic milking stool. As you can see, at any one time it always has at least 3 legs in contact with the ground. Three legs is the minimum number that you must keep on the ground to maintain static stability. One of the earliest attempts to imitate the 4-legged motion of animals was this walking truck, built by General Electric in the USA as far back as 1965. A human operator was suspended in the body, and he gave the commands to each of the legs through a hydraulic system that followed the movements of his arms and legs. This machine was capable of quite impressive feats in the laboratory, tossing a jeep out of the way, for example. But the strain of thinking about which leg to move next exhausted the operator after about 15 minutes, and he had to take a rest. Nevertheless, the walking truck was considered a landmark in the design of walking machines. A major development needed, if only to prevent exhaustion among operators, was some form of centralized control device that could take over some of the decision-making. This Japanese quadruped has a computer, fed with information from sensors that detect where the legs are at any one time and what the surrounding surface is like. Although it has no overall picture of the environment, it will respond to information received from its feet and negotiate obstacles or climb stairs with ease, if not grace. As soon as one of the little wires makes contact with something, it triggers a sort of reflex action to halt or withdraw the leg. The problem with this 4-legged creeping gait is that there's only one tripod. To remain balanced, only one leg can move at a time. A machine with 6 legs, like the adaptive suspension vehicle, can move faster. It has 2 tripods, and this means half the legs can move forward with each stride. It actually moves its legs like an insect in a pattern called the alternating tripod. At any one time, the insect is in contact with the ground through 2 legs on one side and 1 on the other, while moving the other 3 legs forward. Each pair of legs is controlled by its own nerve center, which link up to control the overall walking pattern. It's this system that has been imitated in the world's first commercial walking machine, Odex 1.
Odetics is interested in developing walking machine technology because there are a number of applications where a machine that provides its own locomotion by walking on legs is a very definite advantage where other concepts fail. An example of this is inside man-made facilities, such as nuclear facilities, where the facilities were originally designed for access by human beings on foot, which means stairs and ladders. And these facilities now, of course, are operating with environments where humans can no longer go into these areas, yet there's the need for a machine to go in and do inspection and maintenance.
ODEX-1 is radio-controlled, although it takes care of the guidance of its own legs. It can go up unfamiliar staircases and negotiate doorways. One day, it will have a sense of vision so it can see for itself where to go. The ability to avoid obstacles is essential if the machine is to work with man.
In the man-made environment where the accessible pathways for the robot are very confined and very cluttered, it's extremely important that the walking machine be able to place its feet at very precise locations based on the available foot space. For this reason, we have opted to build a statically stable walking machine concept. And with that statically stable concept, we've chosen 6 legs because this affords the greatest speed efficiency while still maintaining static stability.
But there's a limit to the speed you can reach when you're balancing on a tripod. On a good day, the tortoise can get up to 0.5 kilometre an hour, and in fact it achieves this by having 2 legs in the air for very short periods. Because of this, the tortoise develops a wobble, but it can't afford to wobble very much. Animals that are seriously interested in speed often have no legs on the ground at all. They balance actively, continually adjusting their balance whenever any one of their legs does touch the ground.
In our lab, we've been concentrating on active balance. And to do that, initially, we built machines that only had 1 leg. A one-legged machine has to balance because it doesn't have any opportunity for static support. That is, you can't spread out the feet in order to keep it balanced passively. So we built one-legged machines. They actually hop instead of walk. And we found that the control of these machines wasn't really too difficult. The control system was decomposed into 3 parts. There was one part that maintained the up and down bouncing motion to produce hopping. There was one part that controlled the tipping and forward translation of the machine, and that was done by choosing where to position the foot with respect to the body during each flight phase, every time the machine flew through the air. And then there was a third part of the machine that kept the body level, and it did that by exerting a torque between the leg and the body whenever the foot was in contact with the ground.
One-legged travel really is a kind of controlled falling, with a computer continually positioning the leg underneath the robot's center of gravity. This is actually easier than walking with 2 legs. This computer figure, modeled on the human walking pattern, shows how the pelvis has to shift from side to side to keep the center of gravity adjusted over the foot that is on the ground. The spot in the center of the figure's chest is a constant distance above the walkway. It shows another characteristic of biped walking, how the center of gravity moves up and down during the stride. To reproduce this pattern in a robot is actually very difficult. This advanced Japanese biped is really quite an achievement. It's able to shift its whole body dynamically from one leg to the other with just about enough control to climb a set of stairs. This robot has a cousin who is slightly better at compensating for imminent collapse by swinging the top half of its body like a pendulum.
Walking's a bit like rolling on a broken wheel. Think of the legs as spokes. Think of the feet as bits of the rim of a broken wheel. As we walk, we travel along on this wheel, but because the wheel is broken, we rise and fall. At one stage of the step, we're high. At another stage, we're low. that means we're gaining and losing energy of height. But also we're speeding up and slowing down. And what happens in walking is that as we go along, we're swapping energy back and forth, from energy of height to energy of movement and back again. It's the principle of the pendulum. And that's fine, provided you don't try to walk too fast. Because if you try to walk really fast, then at this stage of the stride where you're falling, you simply can't fall fast enough because gravity won't pull you down any faster. So above a certain speed, walking becomes impossible. You've got to do something else.
And that something else is running. At the transition between walking and running, one leg pushes off before the other touches the ground. The gait changes to a series of controlled leaps. The body starts to bounce up and down even more than when walking, and the legs have to absorb a lot of energy on landing. They store the energy like springs and return it in the next stride. The gait can change quite suddenly in animals as their speed increases. Some, like horses, show several changes. A walking horse often has both left legs on the ground while both right legs are in the air, and vice versa. As it increases speed to a trot, it changes the phasing of its legs. Now it moves diagonal pairs together, jumping from one to the other. As a trot speeds up to a gallop, the legs adjust their pacing to reach a state where the animal bounds from the back legs to the front, with each pair carrying out the movements of a two-legged runner. The horse changes gait for good mechanical reasons. It is actually using the compliance in its legs to absorb the energy released when its hooves hit the ground.
If you consider the problem of actually walking or running, then you have the problem of having a limb which is contacting with the environment. That is, as you take each step or as you're running, then each leg in turn impacts with the ground. And at each impact, you really want to be able to absorb the energy of impact and to use it in your next stride. And some engineers, for instance Raybert in the United States, is looking at the problem of how do you control a machine in which you actually take that impact energy and restore it back into the running gait of the machine when running.
In hopping machines, we use compliance in two ways. One is the feet are soft so that when the foot hits the ground, there isn't a large shock. Then there's another spring in the leg, which is used to give the bouncing motion efficiency, because the energy that's available in one hop is stored in the leg and then returned to the bounce that occurs on the next step.
The springs in the monopod are analogous to the tendons in our own legs, ankles, and feet. Similar material in the locust jumping leg stores up energy needed for its prodigious leaps. In the kangaroo, the massive tendons in its leg make hopping very energy efficient. If we look again at the horse, we can start to explain why it has to change gait. When it changes from a walk to a trot, it starts to harness the compliant properties of its tendons as springs to store energy as it bounces up and down.
Here I've got a model of the lower part of a horse's leg. Here's the hoof, here are bones, and here down the back of the leg, there are the tendons. Now when the horse puts its foot down on the ground, puts its weight on its foot, the joints bend, the tendons are stretched, and then as the step continues, we get an elastic recoil, and the tendons throw the horse back up into the air.
The springs in the legs are used to conserve the energy of the body bouncing up and down. But as the horse moves faster, more energy is wasted, just in swinging the legs backwards and forwards. To conserve that energy, it changes gait again to the gallop, and this brings a second set of springs into play.
Now, the second lot of springs are represented in this model by this piece of rubber here. In the real animal, it's a sheet of tendon running along the back. When the back bends, this tendon is stretched, and then the tendon recoils and makes the back spring back again. So that when the animal gallops, it's bending and extending its back, stretching the tendon and allowing it to recoil. The spring action of the tendon is helping to keep the legs swinging backwards and forwards.
The legs themselves have an energy-saving design. The horse has most of its leg muscles in its rump. This is some way away from the lightweight hooves, which the muscles cause to accelerate and decelerate. In this way, the parts of the horse that undergo the greatest changes in speed are also the lightest. In fact, changing gait is a bit like changing gear. With each change, the horse brings in a new set of springs to make the most economical use of its available energy. Galloping like a horse is one way a robot could achieve greater speed. This galloping quadruped won't win the Grand National yet, but it could be another major step in the design of mobile robots. Its increased speed is helped by the latest in computerized balance systems, relying on sensory information from its limbs and body.
One of the technical ideas behind the walking truck was to use force feedback to give the operator a greater sense of interaction with the machine and the machine as it worked in the environment. The idea was that not only could the operator manipulate handles and pedals to cause the legs to move, but the environment could exert forces on the legs, and those would be fed back to the operator, so he would feel a fraction of those forces. And this allowed him to work much more intimately, and eventually led to dexterity and agility in the control of these machines.
Modern walking machines have sensors in leg joints to tell them where the legs are. There are also sensors in the feet to tell them if they hit anything and when they are touching the ground. Manipulators like the Utah hand also use sensors in the joints to keep track of where the fingers are.
There's a second kind of sensor that measures the behavior of the machine with respect to the outside world. And for us, the most important of those is the gyroscope. The gyroscopes measure what the orientation of the body is in space with respect to the vertical, and also what the facing direction of the machine is with respect to the direction of travel or with respect to the walls of the room.
These principles have enabled this biped to come up with some very impressive robotic acrobatics. It's really more self-reliant than it looks. The connecting pole is just to steady it when it's still. With a gyroscope to keep it balanced, the monopod is more than a match for the provocations of its inventor. The value of gyroscopic balance becomes clearer when things go wrong. This biped can detect when a somersault is about to fail and work out how to regain its balance without looking foolish. This ability to maintain balance is one that many different animals have brought to a fine art, and they often use the principle of the gyroscope. Birds can hover very precisely because they have a sense of absolute position in space and can correct for any change. Flies, like this daddy longlegs, achieve the same precision with the aid of knobbly projections behind the wings. In fact, when the fly escaped with his life at the beginning of this program, it assessed the situation and reacted in about 1/50th of a second, making use of 100,000 different sensory inputs to the brain. The first clue to impending danger comes from the 20,000 sensors in the eye. The head also carries feathery antennae. Bags at the base hang down under gravity, letting the fly know which way is up, whilst the antennae themselves detect airspeed as well as smell. The body is covered all over with touch-sensitive hairs. Hairs in the legs tell the fly how much the joints are bent. Those on the feet indicate when they are touching the ground. It's very clear that the information processing side of an animal's daily life is as important as its ability to move fast. Who eats whom often depends on quick sensing and fast acting. Even insect intelligence is a distant goal for machines. The Adaptive Suspension Vehicle and ODEX need human operators to make decisions about the outside world. This arm, developed by the Jet Propulsion Laboratory, selects and copies the movements of an operator linked to an identical master arm. Even the Utah hand, versatile as it appears, slavishly copies the movements of the human operator, fed to it via this glove. But if robots are going to be more than extensions to our own arms or legs, they have to be capable of extracting information from the environment and acting on it. Where can we find a robot that's up to a human task like this? Reading a musical score and turning it into body movements that produce beautiful music. Well, in Japan, in fact. Meet Waybot, making his debut with the NHK Symphony Orchestra in Tokyo. Waybot is the creation of a group at Waseda University in Japan. Its eyes and brain can read and memorize a page of standard music score. It can then analyze what it sees and generate the movements of the hands and feet needed to play the organ's keys and pedals. Within its narrow area of knowledge, it exhibits a glimmer of intelligence and the ability to carry out tasks that require complicated decisions. With the Bach-loving organ-playing robot, the Japanese have presented the world with a glimpse of things to come. Soon, the Waybot will walk and then it will stride intelligently into the future as part of a family of machines with arms and legs, based firmly on the lessons of nature's technology.